Okay. So yeah, no more people. So last class we started looking at the mesh analysis. So let's quickly review what we did last class. So I think the portion on the modified nodal analysis was clear. Do you have any questions? I'll just skip to the mesh analysis portion. Okay, did everybody understand how to populate the matrix for modified nodal analysis? Okay, good. Basically the point is you have so many elements connected to a single node. Okay, based on the stamp for each of those elements, all you have to do is add up all the, what you're doing is KCL at that node, right? So if you write as G times the G times V equals I, okay, you will be able to split this up into multiple matrices which can be added up, right? So the stamp for each element connected to a particular node will contribute to the G matrix, right? And the independent current source matrix. Now we know that for the source matrix consists of only current source values and other voltage source values, for example. Okay, so depending on which element you are representing, corresponding to that row, you will have that particular element. If you have an independent current source connected to a particular node, that will contribute to the right hand side. Okay, if you have a voltage source between two nodes which is giving you a voltage constraint, that could be put in the other node and so on the right hand side and so on. Okay. After that, after finishing up with modified nodal analysis, we also noted that if you have a network of only resistors and you pulled out all the sources, okay, you pulled out all the sources outside the network in this manner. So you are basically defining N as the portion of the network that has only the resistors. Okay, so since this network is linear, the voltage across any two nodes or the current through any one of these elements, any one of these resistors inside the network, okay, can be represented as a linear combination of all the sources driving this particular network. Is that clear? So, for example, Vx could be written as alpha 1 times Ia plus beta 1 times Vb, where Ia and Vb are the current and voltage sources driving this particular network. Okay, and if you had some K sources, it will be a linear combination of each of these K sources. Now, given K unique or K independent situations, okay, sets of values of, when I say independent, what do I mean? When I say unique or independent, in this particular case, what I mean is they need to lead to a unique solution. So, for example, if I gave you the value for 1 ampere and 2 volts, right? Doesn't mean the next set of values could not be 1 ampere and 3 volts. That will still give you a unique solution, right? But if I gave you 1 ampere 2 volts gives you 1 volt here, 2 amperes 4 volts gives you 2 volts here, that is not a unique set of values. And that is what I mean when I say unique or independent in this particular case. So this particular property, okay, the linearity property leads to this principle called superposition principle. Okay, you can apply each one of these K or S, in this case S sources, in turn and find out the voltage or current of interest and then add them all together. That will give you the overall voltage or current that you are interested in. For example, in this case, I could remove Ia. In other words, I make Ia equal to 0, which means I leave these two terminals open. I apply only Vb. At Vx, I'll get only beta 1 times Vb. Okay, if I had shorted Vb equal to 0 and applied only Ia, I'd get alpha 1 times Ia. The overall voltage there is alpha 1 Ia plus beta 1 Ib. Okay, that is superposition in action. Okay, so that is just a small aside because that is going to drive into what we are planning to do after mesh analysis in today's class. Because mesh analysis we won't spend too much time. Okay, nodal analysis we spent a lot of time. the important thing to note is mesh analysis is an analog of nodal analysis. And the point to note, the reason we won't spend too much time on this is because majority of cases nodal analysis is preferred over mesh analysis, and you will soon see why. Okay. So we said there could be a graph, okay, which represents the network, and we are going to consider a special case of a planar graph. Okay. The overall analysis which you apply could be called loop analysis, but the particular case we are going to analyze is mesh analysis, because the loops formed in the network, okay, in the graph on a plane, in a planar graph, are called meshes. Okay, so we are going to call this mesh analysis. We know that if you have b branches, okay, and n nodes, you have b minus n plus 1 loops, unique loops that can be formed, unique set of KVL equations. So we took an example of a graph which looks like this, okay, which is shown on top here, this one, and you can take any tree, okay, so the tree you can choose to take could be this, okay, and following that you could draw three loops by adding the rest of the remaining branches, okay, that would be this, this and this, correct? So I have 3 unique loops that can be formed and 3 independent KVL equations that I can obtain from this particular graph, from this particular tree that I have chosen. You could choose any other tree, okay, and obtain KVL equations corresponding to that. Now what we will see is that the most common tree that is chosen for this, I will give you an example of this graph, would have been this. This is also a tree, okay. How many? I can make one loop like this, a second loop like this, and a third loop like this, okay. I could have completed the loops in this way, with the tree being this, okay. And actually we are going to rewrite the matrix, because last class I did it for this tree, okay. Even though I gave the example of the other tree and showed the loops, I did the example for this tree because you could do it for either case, okay. Both of them will give you the right solution, the same solution. The reason we are going to choose this tree is because if I give you a planar graph, what is natural is to choose these as the meshes. If I had given you many more connections, okay, something like this, what is natural is to choose what is visible, and that is all there is to it. There is no specific order or way in which to choose it, okay. We just chose to write the equations for based on what we can see. It's just visual. So that is what we'll do. We'll take each of these loops and define loop currents I1, I2 and I3 through these, okay. For each of these loops I can define a current I1, I2 and I3 and write down the KVL equations corresponding to that, okay. And the point to note is that the current through any branch, okay, or any edge that borders 2 meshes, okay, will be the difference between these 2 currents in the direction of choice, okay, in the direction in which you are traveling. In the direction I have shown, the current is nothing but I1 minus I3. If I had taken the reverse direction, I would have got it as I3 minus I1, okay. What is the current through this? The current through an edge that does not border any other, a second mesh, would just be the loop current, would just be the mesh current. So this is I2, this is I3, this current is I2 minus I3, this current would be I2 minus I1. It would, if you choose a consistent direction for all the loop currents, and in this course we are going to choose the clockwise direction for all currents. If you choose a clockwise direction, you will find that the current through any element which borders two meshes is going to be the difference between the two. It's always going to be the difference between the two mesh currents. Okay, it will either be IA minus IB or IB minus IA, depending on which direction you have chosen. Okay. So let us go back to our so I name these three nodes 1, 2, 3. This is 0. Okay. So I have resistors R12, R23, R13, R22. I'm going to define loop currents. Okay, these are the three loops I'm going to take: I1, I2 and I3. So this is loop number 1. Okay, these are the three loops. So now I'm going to go around each of these loops writing KVL. So loop number 1 gives me, so I can start from any one node. Okay, so there are two conventions I'm following. Remember, one is that the mesh current flow in, or the mesh current, the direction of the direction, I'll assume that the mesh current flow in clockwise direction. Okay, I'll also assume I'm going to write KVL as the sum of all voltage drops is 0 through when I go around the loop. These are the two conventions I'm following. Okay, so what is the voltage drop across R12? R12 times I1 minus I3 plus R22 times I1 minus I2. Okay, so R12 has a current I1 minus I3, R22 has a current I1 minus I2. Okay, minus VA is 0. This is basically, I'm seeing a voltage increase when I go from 0 to 1, so that gives me a minus VA term. So I'm going to write this as R12 plus R22 times I1 minus R22 I2 minus R1 minus R12 I3 equals VA. So I am again rearranging this in the same form we did for nodal analysis. Bunch of resistors, okay, times the current variables is equal to the set of voltage sources, independent voltage sources. Clear so far? So for loop number 2, let's say I start from 2, okay, and go around the mesh clockwise. Okay, so I have R23 times I2 minus I3 okay, plus VB okay, plus R22 times I2 minus I1. Okay, one of the advantages of choosing this convention is it reduces the matrix to a form where the diagonal elements are all positive. Okay, because when you follow this direction of current being the same as the direction you are writing KVL is the same as the mesh current, okay, and you are assuming voltage drops are positive, or rather sum of all voltage drops is 0, what you get is a matrix form in which all diagonal terms will be positive, all off diagonal terms will be negative. We are used to something like this. Minus R22 times I1 plus R22 plus R23 times I2 minus R23 I3 equals minus VB. And this is what I was talking about. The diagonal term is positive, okay, the off diagonal terms are negative. And for loop number 3, okay, I'll again start from 1 and go clockwise. R13 times I3, okay, plus R23 times I3 minus I2 okay, plus R12 times I3 minus I1. So minus R12 times I3 minus I1. So minus R12 times I1 minus R23 times I2 plus R13 plus R23 plus R12 times I3 is 0. Okay, this is the third equation. And now we can go ahead and write the matrix form of this. The matrix form is going to be R times some I vector is equal to some V vector. Okay, R is the matrix of resistances, I is the vector of unknown currents in each mesh. Okay, V is going to be the source vector which consists of all the independent voltage sources in the network. Okay, let's populate the right hand side. I have VA minus VB and 0. Okay, on the left hand side I have R12 plus R22 minus R22 and minus R12. Now I can also, the minute I know this, I can populate the first column. So I know this is going to be minus R22, this is going to be minus R12. The next diagonal term is R22 plus R23 and minus R23. So this term is going to be minus R23. The last one is R13 plus R23 plus R12. Okay, so this is my system of equations describing this particular network. Any questions so far? Okay, very good. So as you can see, it has, as we saw last class, it has the same form as what you originally had for nodal analysis. Okay, you can form very clear analogies. The diagonal terms are positive. What do they represent? What does each diagonal term represent? It represents the resistors which are contained in the particular mesh for which you write KVL, right? So this corresponds to loop number 1, loop number 2. Just like each row correspondent to KCL at that particular node, at any particular node, here each row corresponds to mesh KVL equations written for any particular mesh or loop. Okay, so for loop number 1, R12 and R22 are the resistors in that loop, okay, in that mesh, and therefore they will appear as positive terms in the diagonal entry, okay, which is first row, first column. The second term will correspond to R22, which is the negative of the common resistance between mesh 1 and mesh 2, okay, and similarly R12 is the common resistor between mesh 1 and mesh 3, okay. So the negative of that common resistance is what will appear in this matrix, okay. Now you can go ahead and look at any circuit consisting of voltage sources and resistors and write down this equation without any problem, okay. Any questions? Okay, so what kind of complications do you expect to arise? First, let's think back to what we did for nodal analysis. What is the first complication that could arise? Current sources, right? In the case of nodal analysis, we had a problem with voltage sources. In the case of mesh analysis, we will most probably have a problem with current sources. Why is that? Because we do not know the voltage across the current source, right? That is not well defined. So VA, VB, and let us say I had a current like this. Okay, let's say I had a current source IC like this. Okay, so of course, if you start to write KVL, for example, for loop 1, you do not know what this VC is. I am going to denote that with a small letter for now, okay, or I could just call it Vx maybe. I don't want to use VC because it looks like an independent voltage source, so I'll just call it some Vx. We do not know the voltage across this current source, okay. So if you start to write KVL for loop 1, Vx will also be an unknown. So what do you do? What did you do in the case of the nodal analysis? How did you handle voltage sources? You define a super node, right? What is a super node? You basically agglomerate the two ends of the voltage source into one single node or into one single system of nodes and write KCL for that. What do you expect you do here? You define what is called a super mesh, okay. What will that super mesh be? This will be the super mesh, okay. Now you are no longer talking of nodes, okay. You define what is called a super mesh. You no longer write independent KVL equations for loop 1 and loop 2. So you will just write KVL for this, okay. You will write KVL for this super mesh. But what happens? What happens when you define a super mesh and write a KVL equation for it? You lose an equation, right? We have seen this for the super node. You lose an equation. Now you need to get one extra equation to compensate for that, to solve the system of equations. What is that extra equation? In the case of nodal analysis, what extra equation did we use? The voltage source constraint, right? The difference between the two ends of the two terminals of the voltage source is very well defined. We use that constraint as the additional constraint. What would you do here? The difference between the currents. It's very clear that IC is the common branch between loops, original loops 1 and 2. Okay, in this direction, the current would have been I2 minus I1. Okay, so I am still going to define my loops like this as I1, I2, and I3. Okay, the additional constraint I get is that IC is equal to I2 minus I1. So the additional equation is I2 minus I1 equal to IC. In other words, the additional equation I am actually writing KCL at this node. Okay, I am writing KCL at this node. Okay, just note that. In fact, in the original case of the super node for nodal analysis, we actually applied KVL there. Even though we were writing KCL for everything else, the extra equation we got from writing KVL. Any questions? Okay. Actually, let me move this to the previous page. I was going to start a slightly just leave it like this. Okay, so I'm actually going to stop here because we don't need much more. You can talk about modified mesh analysis and so on, but it's of probably only theoretical value, right? Any idea why nodal analysis would be preferred compared to meshes? Okay, but what is the, okay, here you said the choice of meshes is not unique, right? What is the corresponding case for nodal analysis? No. If I had actually combined two nodes together, not define a super node, but I had actually combined two nodes together and written KCL for that, okay, that would correspond to a larger loop. Okay, let me take the original circuit. Okay, let's take this original circuit. If I had actually defined this as one of my loops, okay, what would have happened? We saw that it was still given as the same set of KVL equations because you do have independent elements in three loops. Suppose I had used loop 1 as this original loop 1, loop 2 as the one written in blue, and loop 3 as this original one in black. I would have still got the same solution. Okay. What does this correspond to? I am basically writing KVL for the overall larger loop combining loops 1 and loop 2. That is the super mesh we just defined, right, when you had a current source. In the case of the nodal analysis, that would have corresponded to writing KCL for two or more nodes put together. So there is nothing unique about this. You could have done that. As long as you ensure that you are choosing unique set of super nodes, that's okay. So that is not the difference. Any other ideas as to what could be causing this problem? Actually, there is no problem. I can extend this to, I hope you realize this is mesh analysis. Okay. I can extend this to what is called loop analysis. There is nothing that prevents me. Is there anything that prevents me? KVL is always valid. Okay. When you start from one point and return to the same point, KVL is always valid. Okay. What prevents me from, doing this for non-planar circuits? No, more equations is okay. That is not the issue. Primarily, okay, from what I understand, okay, I'll tell you, it is a problem of visualization. Okay, we are very comfortable with circuits that can be drawn in a planar way. Okay, we can clearly identify the loops. If I had a non-planar loop, okay, and I want to write KVL for that, it is very difficult to visualize it on a planar when you are representing the circuit in a planar way. Nodes, on the other hand, even if the circuit is non-planar, you are starting from a single point. You know what all connections are available from that point. So if I had actually given you a connection, let me copy this. So let me make this suppose I wanted to connect like this. Okay, I make that connection. Sorry, maybe I shouldn't make it as short. So I made this connection. Okay, I also want to connect. Okay, let us say this guy to this guy. I have to put in a crossover, right? I can put in the crossover like this. So this is Rx and this is Ry. Now do you see how if you start drawing non-planar circuits, it's actually very difficult to visualize the loops that are going on, okay, that are part of this. If I were just writing KCL at these nodes, okay, I know exactly what these connections are. It is much easier to visualize it. Okay, that is the only difference. You can always write KVL for all possible loops, even for non-planar circuits. Okay, it is possible to solve the set of equations. Okay, so the rest of it, adding control sources and so on, you can always do this. What is the biggest source that was a problem for nodal analysis? Current control sources, especially current control voltage sources. Right, you had to define maximum number of variables for current control voltage sources because the current through the voltage source was an unknown, and you had to define a pseudo node for the controlling current. What do you think will be the problem here? Voltage control current sources will be a problem here. Exactly the opposite problem. The voltage across the current source is unknown, and on the input side also you will have a problem. Okay. So anyway, that's just of academic value. I mean, okay, not academic value, it's of theoretical value. Of course, you are interested in things of academic value. Okay. So we'll move on from here. So we are kind of done with nodal analysis and mesh analysis. Any questions on this subject so far? Okay, very good. So we are going to start a new set of topics. Okay, we are going to deal with circuit theorems. Okay, there are actually a whole bunch of theorems with respect to circuits. Okay, and networks. So let us say I have a network N. Okay, consisting of, so I'll say resistors, independent voltage sources and independent current sources. Okay, this is the network consisting of resistors, independent voltage sources, independent current sources. Okay, and this resistor is also part of the network. I am just pulling it out for now. Okay, I am just looking at one resistor in this network. Okay, let us say the voltage across it was VR, and let us say the current was IR. Okay. Now suppose, so this particular network will have a steady state, okay, corresponding of a set of voltages and currents corresponding to each element in this network, whether it's the current source, voltage source or resistor. Okay. Now what I want to do is see if is there any way of replacing this resistor with something else such that the system of solutions does not change. So you understand the question? I want to remove this resistor and put in something else here, okay, such that the set of voltages and currents describing the steady state of the network does not change. Okay, if I had picked another element inside this network which had a certain voltage and current across it, that should not change, and this should be true for all elements. Any idea what this could be? Okay, so he says a voltage source and a current source in parallel. Okay, let us see that. What is the direction of the current source now? Downwards. This is VR and IR, is that what you mean? So let us say this is 1 and 1 prime. So he suggests this could be a possible solution. What do you think? Is this a possible solution? Why not? Huh? it can be a current through the voltage source. What is this equivalent to? A voltage source in parallel with an IR. What is this equivalent to?
Near VR, we can add another current source, but it will have zero current.
But that's just a wire. Or it's actually an open circuit, sorry. A current source with zero current is an open circuit. We have seen this before. Okay. Now what is this? First of all, let's finish this and then we can come to other suggestions. What is this equivalent to? This is just a voltage source. We have seen this before. An ideal voltage source in parallel with anything else is just the voltage source itself, because the constraint is exactly the same as before. Between 1 and 1 prime, as soon as you connect a voltage source VR, the voltage between those two is completely restricted to VR. Okay, because the current through VR can be anything. Okay, this is just equivalent to the voltage source itself, because any difference in the current would just flow through the voltage source. So you understand. So if I had, this is the same as if I had connected VR through this. Okay. If the rest of the circuit was trying to set a current which was different from IR, the difference between the currents will flow through the voltage source. Okay, I hope you see that. That is not what we want. So this is anything you add in parallel with an ideal voltage source is the same as the voltage source itself, as far as the rest of the network is concerned. Obviously, as far as VR is concerned, there is a difference in the current. Okay, as far as the rest of the network is concerned, it's exactly the same. Obviously, I can also tell you, if you try putting VR in series with IR, that will also give you the wrong solution, because anything in series with an ideal current source is the current source itself. Okay. So I can also tell you that if you try this, so this is the same as IR, because the current source can accept any voltage drop across it. So whatever the voltage between 1 and 1 prime, the difference between that and VR will fall across IR. So any other answers? Neither of these two is the solution. Okay? Or rather, if either of these two is the solution, you need to tell me why. You put the resistor in series with R.
You put another two resistors in series at ground bar.
No, but that is not what I want, right? I want to connect something else here which will not change this. What you are saying is two resistors. That is just such a trivial solution, right? I want something else. Okay, so let us see what can do that. Actually, forget about 1 and 1 prime. So this is I0 and this is also I0. What will this look like? So let us say there is some resistor R connected like this. What is the current through the resistor R? Why is that? Of course, you know, you can write KCL at these nodes, and you can show that the current flowing through the resistor is 0. Either of these two nodes you write KCL. So the current from the first current source is going to all completely flow through the second current source. Correct? So the current here is 0. The current here is 0. Okay? So suppose I took my network N, across which I had my resistor R, okay, and so this is IR, this is IR. Okay, what is the current through these two? 0. Okay, because between the same current will tend to flow between the two current sources, and there won't be any current in these wires connecting this network to those two set of current sources. Okay, so suppose I take this guy, I'm just going to redraw it in this manner. Okay, can you tell me what the current here is now? I've just redrawn the same circuit. Okay, I've just swapped one of these current sources with the resistor. What is the current through those two wires now? What is this current? IR. Okay, so this current is IR. I have not changed the network, remember. Okay, I have not done anything. We agreed originally that these two current sources placed in this way, okay, cause zero current to flow outside, flow in or out from this particular network, okay, from any particular network connected to that. The next step I did was take that and connect it to the original network, okay, across the resistor, and we said, okay, the same thing should hold, there should be zero current through these two, okay. Then I just redrew the same network, okay, by these two are just in parallel. I can just draw it in this manner. The current coming out of the network should not change as before, so it's the same IR flowing out, down. What is now the current through these two wires? It should be 0, right? You can write KCL at these two nodes. You can write KCL at these two nodes and show that the current through these two wires is 0. Okay? If the current is 0, what can I do to those two wires? If I open up those two wires, what will happen? Nothing. Right? If the current through those two wires is 0, if I open them up, nothing will happen to the rest of the network. Okay? So, if I did this, okay, nothing will happen to the rest of the network. What does that mean actually? What is this voltage? Has to be VR. Okay, this voltage will still remain VR. Okay, inside the network the state of all the other voltage and current sources will remain the same. Okay, so nothing will change as far as the network is concerned. Is that clear?